you're going to need your own copy of the... Whoa, I can't believe how white I am. My God, I've got to get out into the sun a bit more. So pasty. Mind you, no such thing as a healthy suntan, they say. You're going to need your own copy of the paper. So here we go. The average was 23.75 out of 50 for this. Less than 50%. So the first one is excess and limiting. So I've got 3.26 grams of iron. And what I need to do is I need to find the moles of iron and the moles of copper sulfate and then see which one there's too much of and which one there's too little of. So moles is mass over molar mass. So what's the molar mass of iron? 55.85 grams per mole. So simply divide those numbers. Moles is mass over molar mass to get the moles. So I'm going to keep 4 sig figs and then round off to 3 if I need to. Oh, I got a message. 05837. Now it's tempting to also put that number into this box because it's one of those is one of those, but no. This is excess and limiting. The numbers in the moles, the number of moles is going to be different. It's not going to fit that pattern. So the moles of copper sulfate, well, it's a solution. So moles is concentration times volume. Concentration is given in the question, 0.200, as is the volume. Now the volume should be in decimeters cubed, so divide by 1,000. So let's see the moles of copper sulfate. So that's going to have 3 significant figures. So it's 0.0160. All right, so they ask you which one is excess and which one is limiting. You might just be able to do it by visual inspection, as we say. So 1 iron needs 1 copper sulfate, and it seems plain that there's way more iron than copper sulfate here. So indeed, copper sulfate is the limiting. That's the one that runs out first. And you get the point for that just by identifying it. Sometimes they ask you to explain why. So allow me to just explain why. So you put iron and then you put the copper sulfate. Now if you divide the number of moles, 0.05837, if you divide that by the coefficient, in this case 1, that gives you 1 number for the iron. For the copper sulfate, do the same thing. 0.0160 divided by the coefficient. Now you have to look at those 2 relative values, which is bigger, which is smaller. Well, it seems clear that copper sulfate has a smaller value than iron. So lower is limiting. That's how I remember it. Lower is limiting. So then you just have to say that the copper sulfate is limiting. You've just proved it. All right. Work out the percent yield. Again, it is tempting to go, oh, it says there's 0.872 grams of copper. So that's the mass of copper. No. That's the experimental mass. That's how much the experiment got. This table is for theory, like T for table, T for theory. It's the theoretical. So if I'm going to work out the percent yield, I'm going to need to know the theoretical mass that I should have made. Well, since the copper sulfate runs out first, that's how many moles I've got. So that's also going to be the same number of moles of iron 2 sulfate, which is also going to be the same number of moles of copper, 0.0160 moles. And I like to put a big X and an S through the things as excess. The big X to remind me, no, that one's wrong. In fact, that's going to be wrong as well. That's way too big a value. So how are we going to work out the mass of copper? Well, mass is moles times molar mass. So what I'll do is I'll look up the molar mass of copper, 63.55 grams per mole. So put that in the box, 63.55. Now just simply work out the mass. Oh, that's nice. So maybe I'll keep that 4th significant figure as well, but I think that's probably a bit of a waste of time. in case I have to round off. 017. 017. All right, so that's about a 1 gram of copper that I was expecting. So to work out the percent yield, so percent yield is the experimental mass over the theoretical mass times 100. The experimental mass was that. The theoretical, the one from the table, was 1.017 grams multiplied by 100. So it looks like to 3 sig figs, so that's going to be 85.7%. Cheeky check of the answers. Oh, they got 85.5%, but they'd absolutely accept anything between 85 and 86%. Well, I like my answer. Challenging, eh? Yeah, I think that's because they cocked up this question. Looking at the examiner's report, they tacitly acknowledge that too. All right, so temperature rise, calorimetry. So for calorimetry, you're going to be using this equation, Q equals mc delta T. Shouldn't be chewing a sweetie while doing this, but it's nice. So Q is energy, M is the mass of what you're heating. I have to spit it out. Come back to that later. C is the specific heat capacity of what you're heating, and delta T is the temperature rise of what you're heating. Well, what you're heating? Well, you had 80 milliliters of copper sulfate that turned into iron sulfate, wasn't it? Yeah. So you're heating probably some exotic cocktail like that. Also, what's the mass of 80 milliliters of iron sulfate then? Well, it's 80 grams. We're going to assume it has the same density of water, where 1 milliliter is 1 gram. So the mass, 80 milliliters. Nope, we're going to assume that's 80 grams. Well, here's your first problem. For the specific heat capacity, are you going to use 4.18 or 4.18? They're different 4.18s. The answer is supposed to be in kilojoules, so you better use the first 4.18, which relies on kilograms. So 80 grams isn't going to cut it. It has to be 80 over 1,000 kilograms. Specific heat capacity, I'm just going to assume it's water. So that's going to be kilojoules per kilogram per Kelvin. And the temperature rise is 7.5 degrees C, which is the same as the temperature rise of 7.5 Kelvin. All right, so let's work that out. So 2.51, and that's where I thought it ended, kilojoules, which is what they asked. But then now they're saying, oh, in the examiner's report, we wanted it in kilojoules per mole, but we didn't put that, and I think they should have cancelled this question. Well, let's carry on. So then we'd have to do delta H is Q divided by moles. Okay, well, that's just weird. So Q is a 2.51, and the moles, well, the moles of what? Well, it's going up to the balanced equation. It's going to be the moles of copper sulfate. Well, to be honest, all the moles are the same, so whichever one you chose, except for the excess, which we crossed out. So 0.016, 0.016. So 2 sig figs, the 7.5 kelvins locked me into 2 sig figs, so it's 160. So it's 160. Now I think that's in kilojoules per mole, but the IB doesn't. I'm pretty sure I'm right. Anyway, you still don't have your point, because you need the minus. I wouldn't worry too much about that question. I think it's a bit of a disaster. There's another stinker coming as well. So what assumption did I make? Well, the assumptions that they want you to say is that there were no side reactions. You didn't make anything other than the two chemicals produced. You assumed that the density of the solution was the same as water. 80 millilitres is 80 grams. What else have we got here? You also assumed that the specific heat capacity was 4.18, which is the same for water, even though it wasn't water, it's mostly water. And the reaction goes to the completion, that you gave it enough time to finish. There are other legitimate assumptions you could have, but they're not rewarded with points. For example, what about that lump of metal you got stuck at the bottom? You made some copper, didn't you? We didn't take into account that. They don't like that. I don't think I've seen that for a while on the mark scheme. Don't like that part of the question either. The next part of the question, I am pretty sure their answer's wrong. So if the only uncertainty is the temperature, so I'm going to work out the percentage uncertainty. It's 0.2 over 7.5 times 100. I know it doesn't need to be the percentage, but I like the percentage, so we'll just do the percentage first of all. So 0.2 divided by 7.5 equals times 100. Now the IB rounded that to 3%, which then screws up the numbers later on. I'm not going to round just yet because I'm not finished. So I'm going to say it's 2.7%. So if my thermometer is out by plus or minus 2.7, then my final calculation of minus 160 could be out by up to 2.7%. So let's work out 2.7% of my 160. And so that gives me 4.3. So that gives me 4.3%. So the uncertainty is plus or minus 4.3%. Now, traditionally the IB wants you to have uncertainty to 1 sig fig, so it will be plus or minus 4, but in this case it's wrong. So there's some inconsistency there as well. They want plus or minus 4.3%. They'll even take plus or minus 5%. Well, how the hell do you get that? By over rounding that to 3. That's the third part of this question in a row that I think is just not fit for purpose. Come on, IB. Next question. Well, you started off with no copper sulfate.
And then you made a bunch, so it's going to be this curve here.
1 point for saying at time equals 0, there's none of it. And the second point is for showing that the gradient gets less and less steep until it's flat, which shows that the reaction's slowing down. Of course it's slowing down. There's less reactants, less collisions per unit time. So that's your 2 points there. How could you get the initial rate from this graph? Well, initial rate's going to be at time equals 0, isn't it? So time equals 0 is, well, that's here. And the rate is the change of the concentration of reactants over time, or the change of concentration of products over time. So let me draw in a tangent. Oh, that's pretty good, but I could do better. I could do better. Nice. And so if you then worked out the rise over the run, that will give you the initial rate. Is that enough for my 2 points, Mr. IB? Yeah, you've got to draw a tangent at time equals 0 and then just say it's the gradient or the slope. Okay. Well answered. Thank you. Excuse me. So you've got iron powder or you've got a dirty great big iron lump. So collision theory. 3 parts of collision theory. For a successful reaction, the reactants have to collide in the correct geometry with energy equal to or greater than activation energy. So the reactants, the copper sulfate can get access to pretty much every piece of iron if it's powdered up. But if the copper sulfate would have real trouble getting anywhere but the surface of that lump of iron. So a lot of iron's hidden inside, so it's to do with surface area. So for 2 points, I'd say that the lump of iron has a smaller surface area, and to bring in collision theory, that means there's going to be less successful collisions per unit time. If you just say collisions, you don't get the point. If you say less collisions, you don't get the point. You have to say less collisions per unit time, or less frequent collisions. They're fussy, and rightfully fussy about that. Next up, propan-2-ol. Structural formula, so you can't be doing that. That's the skeletal structure. That's a bit cheeky. That wasn't allowed. So prop is 3 carbons. 1, 2, 3. And I've got the OH coming off of the second one. If you forget any hydrogen at all, you'd lose the point. Fair enough. I think that's in Purell hand sanitizer. Maybe that's prop-1-ol. How many hydrogen atoms in 1 gram of propan-2-ol? So for these sort of calculations, if you end up with a number like 4, that's probably wrong. A gram of Purell probably has more than 4 hydrogen atoms. It has to be a thumping great big number. Most people got it. All right, so let's have a little think. So I think first of all I need to work out the molar mass of propan-2-ol. So the molar mass of propan-2-ol. I'm going to use the integers, and I'm sure I'll get away with it. So I've got 3 times 12, because the molar mass of carbon's only a little over 12. And then I'm going to have a 16 for the oxygen, and then 1, 2, 3, 4, 5, 6, 7, and then 8 for the hydrogen. So what's that going to be? 24, 34, 44, 54, 60. That's nice. So it's going to be 60 grams per mole, and I'm playing fast and loose with the sig figs. So if I've got 1 gram of propan-2-ol, how many moles is that? Well, so moles is mass over molar mass. And so I've got 1 over 60. I've got 1 over 60 moles of propanol. So how many particles in 1 mole? In 1 mole there's 6 times 10 to the 23 particles. So in a 60th of a mole, well, let's do some cross multiplication. So I know that 1 mole is 6 times 10 to the 23, again fast and loose with the sig figs. So actually now I've got a 60th of a mole. I want to know how many particles I have. Let's say particles. I've got a feeling that that's easier than it's supposed to be. I'm not going to use my calculator, see if I can do it with my brain. So the 60 goes at the bottom. So 1 over 6 times 10 to the 23 over 60x. And then so 6 times 10 to the 23 plus 60x. So divide by 60, get rid of that. So that becomes 1. Divide by 10. So I think that means there's 1 times 10 to the 22 particles, or propanol molecules in this case. I'm going to quickly check. All right, so that's how many molecules of propanol I've got. Now, the question wants me to wants me about, speak English for me. The question wants me to, the number, how many hydrogen atoms there are. So what I'm going to do is I'm actually going to now multiply that number by 8. So I'm just going to erase that. I'm going to multiply the number by 8. Why 8? Because there's 8 hydrogens. So I think that's going to come out at 8 times 10 to the 22. Let's hope they don't want the sig figs. 8 times 10 to the 22. Accept answers between this and that. And I don't think there's a penalty for sig figs. Thornley win. That's it. So again, it's got to be a big number. If you've got a small number, you've got something upside down somewhere. All right. Primary, secondary, or tertiary? So, this is how I do it. Find the OH. Find the carbon attached to the OH. How many carbons are directly attached to that? There are 2. So this is a secondary alcohol. I think that way of explaining it's pretty clear, but I bet the IB doesn't like it. I bet they're going to say something like, because the carbon attached to the hydroxyl group has 1 hydrogen. Oh, no, they'll take my dodgy answer too. Dodgy, it's not dodgy, it's correct. Okay, so either of those answers will do. Nice. Next up, oxidizing agent for the alcohol. So that's going to be acidified dichromate solution. I remember that was my first explosion. Scared the hell out of me. I put in the orange stuff, it blew up and it turned the ceiling green. So I can even remember the colour change. So let's say it's acidified dichromate solution. Now sometimes they might be a bit fussy. They might want you to say dichromate 6. Let's see if they're fussy about that today. Dichromate 6 is what they need. Okay, so dichromate 6. Or they would also accept the formula Cr2O7 2-. Well, where the hell does the 6 come from? That's the oxidation state of the chromium. That's interesting. They don't often ask for the 6. So we'll see. Oh, the oxidation state of carbon in propan-2-ol. Well, that's what have we got? We've got CH3, CHOH, CH3. Oxidation state rules. So oxygen is -2 in a compound. Hydrogen is +1 in a compound. There's a couple of exceptions, but none of them apply here. It's all got to equal the charge on the compound. Sum up to that, so it's a 0 charge, it's a neutral molecule. Isn't that -2, -2, -2? Yeah, so the answer is -2. The electron configuration of the bromine atom. All right. Oh no, hold on, we missed one out. Oxidation of propan-2-ol. So essentially what happens is the OH turns into a carbonyl group. That's tempting. I almost put one in the middle there, but that would be crazy. That would be a pentavalent carbon. Now, do they want the name or the structure, or what do they want? That's the product. Oh, I drew the structure. So that's called propanone. Right. Electronic configuration of bromine. Well, let me see how many electrons it's got. So bromine has 35 electrons. Well, let's do it on here. So counting along from block to block, just going to light up. So I've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, 1, 2, 3, 4, 4p5. I don't think you can just draw the circles though. And rather generously, they'd even accept if you did the shorthand version, which really isn't what they asked for. That's rather generous of them. Oh. Which would be 4s2, 3d10, 4p5. Okay. Disappointing. Okay, I'll take that. Disappointing. Sketch an orbital diagram of the valence shell of a bromine atom, ground state. So the valence shell, it's in period 4. It's got electrons in the 4th shell. So let's have a look at those. I've got a couple going around in a sphere and 5 of them going around in a propeller shape. Well, if it's asking is it for orbitals, so orbitals are boxes. So I've got the 4s there and a couple of electrons. And then the 4p is going to be at a higher energy. That's got 3 boxes and it had 5 electrons. 1, 2, 3, 4, 5. Oh. 5. Oh, come on, Thornley. 5. Is that right? That's right. Okay, moving on. Draw the Lewis structure for the BrO3 ion. All right. I've got to stop saying all right, it's annoying me. Sorry about that. I'm saying sorry. Oh, I'm so British. So bromine is in group 17, 7 valence electrons, and oxygen is in group 16, it has 6 valence electrons. And there's 3 of them, plus a cheeky bonus electron there. So I need to know how many valence electron pairs there are. So if pairs, you've got to divide it by 2. So what is that? 18 plus 8, that's 26, that's 13. So I got 13 electron pairs to distribute. Bromine goes in the center because it's the first one in the formula. And then separate the others evenly around the outside. Now it says it's octet. Okay, so I'm just going to draw in 3 to start. 3 pairs of electrons. And I have 10 more to distribute. Well, I'm just going to throw them in, see what happens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, okay. You might not get the point unless you put the brackets and the minus. Are they going to ding you for that? Yep, you have to put the brackets and the minus. Let's just double check. I should have 13 electron pairs. Yep, and every atom is surrounded by 4 lines, which is the same as which is the same as 8 electrons. So a line is a pair, 4 lines, 8 electrons. What's the geometry? The geometry, well, that to me looks a little bit like, it looks like the geometry of ammonia, doesn't it? So if you remember, the geometry of ammonia was a trigonal based pyramid. Trigonal based pyramid. And why is that? Well, the central atom has 4 electron domains, 1, 2, 4, and 1 lone pair. That's your answer. You don't need to mess about with anything more than that, I'm sure. So the central atom, it has 4 electron domains and 1 lone pair. Let's check the answers. It's got to be right, come on. 4 electron domains. Nice. Oh, and they want the angle as well. Well, if it was a regular tetrahedron, it would be 109.5 degrees, but that lone pair of electrons is repelling the bonded pairs down, so it's going to be 107.5 degrees, isn't it? Just like ammonia. Yep. 20% correct, eh? Okay, so bromate ions, BrO3-, bromate 5, turns into bromide ions. Now there's no way that you're going to balance that unless it's in acidic solution, which it is. So acidic solution means, first of all, you've got to fix up water, add it where you want to make it balanced, then hydrogen ions, that's the solution, that's the acidic, and then balance off the electrons at the end, in that order. Okay, so if I add 3 waters to the product side, I've now balanced oxygen. There's 3 oxygens on each side. And if I then add 6 hydrogen ions onto the reactant side, I've now balanced off the hydrogen. But it's still not an equation because the charges on each side aren't the same. So if I add 6 electrons to here, now overall, each side of the equation has a charge of -1. Is Is that right? Yeah, I didn't put state symbols in, but they didn't ding you a point if you didn't either. Okay. Now it reacts, turns iron 2 into iron 3. All right. So the other equation is iron 2 plus turns to iron 3 plus. And again, that's not balanced. I don't need water or hydrogen ions, but I do need an electron. I'm going to stick the electron on there. Okay, now each side has a charge of +2. Now, if I'm going to combine those equations, I've got to get the electrons to be the same. So I'm going to multiply the equation at the bottom by 6, giving me 6 electrons at the top equation and 6 electrons now on the bottom one, which means I can then add them. Your electrons should be on opposite sides. If they're not, you haven't flipped something around, or you flipped it around incorrectly or something. All right, so let me add that up. So I can cancel those 6 electrons and those 6 electrons, and that gives me the bromate 5 ion, 6 hydrogen ions, 6 iron 2 plus ions, got some bromide ions, 3 waters, and 6 iron 3 plus. It's going over my face there, isn't it? 6 iron 3 plus ions. Is that right? Bromate 6 and 6, and bromide and 3 and that. Yep, only 30% of people got that correct. I don't like all of chemistry, but I kind of like that stuff where you put all that together. Question 4. Why does the atomic radius get smaller from sodium to chlorine? So looking at the periodic table, so sodium is big, that's got 3 shells, all the way over to chlorine, which still has 3 shells, but it's smaller. Now there seems like a bit of a paradox going on here. You're adding, as you go across, protons, neutrons and electrons, you're adding more stuff. So why is it getting smaller? Well, of course, if you're adding more protons and electrons, there's going to be more electrostatic attraction. And so that attraction is going to cause the atom to get smaller. So that's the reason why. That would be the first point. And almost certainly the second point is you have to say the electrons are added to the same shell. Because if you go down, as you go down, you're adding more protons, neutrons and electrons, and it's getting bigger. Well, that's because you're adding to increasingly higher energy level shells. So that's the 2-point answer, I bet. So as you cross the period, there's more electrostatic attraction. That's just a clever way of saying plus attracts minus, so between the protons and the electrons. That's the first point. And the second point is there's the same number of shells, or added electrons are added to the same shell. Okay, that's my 2 points there. That comes up most years, a variation of that. So why is the sodium ion smaller than the oxide ion? Okay, so I'm going to do sodium and then I'm going to do oxygen first of all. So sodium is 281, let's go old style, and oxygen's 26, and that's smaller. Okay, so if sodium's the plus ion, that means I can remove 1 electron, so that one there's gone, so it's going to be 28. And oxide has 2 extra electrons. Oh, so I'll add another 2. So they're both 28. So you might naively think if they both have 10 electrons, then they'd be the same radius. But that's not true. So what else is different about them? Well, sodium has 11 protons, pulling in those 12 electrons. But oxygen only has 8 protons, pulling them in. So is there more attraction between 10 electrons and 11 protons? Or is there more attraction between 10 electrons and 8 protons? Well, the 11 protons are more attractive, so that's why sodium has a smaller radius. Same number of electrons, but sodium has an increased nuclear charge. Is that my 2 points? Same number of electrons and more protons in the sodium ion. Correct. Okay, I'm not going to write that down. Physical properties of sodium oxide. So sodium oxide is a metal and it's a non-metal. So almost certainly that means it's ionic. So just like salt and things like that. So let me think of the physical properties of salt. Well, it's white. Well, it doesn't really count. That's just not really helping. It has a high boiling point. Ionic compounds have strong bonds. So I bet it has a high boiling point. Yep, maybe even a high melting point. I bet it's a solid at room temperature, again, because it's got high strength ionic bonds. I bet it's an insulator as a solid, and it conducts electricity when it's molten, or if it dissolves in water. Yep, nice. Don't give any chemistry, you stick it in water, it becomes basic. That's a chemical property. Question 5. So why is the equilibrium homogeneous? So homo means same. So what's the same about this? Well, the states of the products and the reactants are the same. That's the answer they want. But if you say the states of the products and the reactants are all gases, some years they give it to you and some years they don't. Let's check this year. It says they're all in the same phase. That's the point. But if you say they're all gases, they'll give it to you too. That was nice. All right. So only 50% of people got that correct. Of course, heterogeneous means that the products, reactants, well, they're going to be in different phases. Maybe one's a solid, one's a liquid. 5b. Now it looks like equilibrium hasn't been established because you've just thrown all these things into the flask. So instead of using the equilibrium constant, Kc, you're going to use Q, the reaction quotient. Well, so it's the same kind of setup. Q is the concentration of the products. What was the product again? Sulfur trioxide. The concentration of the products over the concentration of the reactants. And were there any? Yeah, so I need to put a squared here and a squared there. So let me work out this value for Q, the reaction quotient. 0.5 squared. I'm keeping the sig fig straight in my head though. 0.2 squared times 0.3. That's 0.25 over 0.04 times 0.3. So that's going to be 0.25 divided by 0.012. Can't do that, Miad. Okay, so I'm going to stick with the 3 sig fig, so that's 20.8 is Q. Yep, predict the direction showing you're working. So the direction is going to be forward or backwards. So for the original, Kc is 280. So when it's at equilibrium, it's 280, which means there's a lot more of the products than the reactants. But in the example we just saw, it was 28. It's supposed to be 280. So that means the reaction must be continuing to move this way as equilibrium's established, to turn that 28 into 280. So I think, what's the question? The direction. I think it's going to the product side. And the reason why is because Q is smaller than Kc. So I think since Q is smaller than Kc, it's moving towards the product side. I don't know how they phrase that. Oh, got a message. Proceeds to the right. I can never remember that. So it's proceeding to the right. Proceeds to the right. I don't think you should be saying shifting because that implies equilibrium's established. Okay, so I probably would have lost a point there for my terminology. 40% got that correct. Okay. Butanoic acid, oh, that smells terrible. It smells like smelly feet. And ethylamine. So each of the substances with water, so you've got to put the equilibrium sign in. How do you know that butanoic acid's a weak acid? Well, all organic acids are weak acids. Or you could just remember hydrochloric acid, sulfuric acid, nitric acid are the strong acids. Everything else in IB is weak. So if it's an acid, it's going to lose an H plus, isn't it? So let's put that H plus on the water. And then what have I got left? If I've removed that H plus, what have I got left? CH3, CH2, CH2, CO2 minus. Formatting could be better. And what about this ethylamine? You've never even heard of that. Most teachers don't mention it. I don't think I mentioned it. Well, it does look a bit like ammonia, doesn't it? If you were to knock that off and put another hydrogen on, it's basically ammonia, and I'm sure you covered that. So for ammonia, that's going to grab an electron to go to ammonium. Excuse me, grab a proton to go to ammonium. Jeez. So I've got my CH3, CH2, NH3 plus, and don't forget it's a base because it's like ammonia, and pretty much all bases make this hydroxide ion. So a hydrogen ion goes from the water to there, just like ammonia. Is that right? Yeah. Got to have that equilibrium. And again, I didn't put the state symbols, but no penalisation for that. This question was discriminating. Only the better students got it. 6B. This is another question I just don't like. So butanoic acid's a liquid. Ethylamine's a gas. I'm just going to read the answer. I don't necessarily agree with it. So if this is a liquid, then this must have greater intermolecular forces. Okay, I'll go with that. Greater intermolecular forces. And they say that the reason that is because it's got either more hydrogen bonds, more H bonds, or it's got stronger H bonds. Okay. Well, that just doesn't feel right, does it? Because if you look at the structures, this NHH, that seems to have the capacity to make 2 hydrogen bonds here. But then looking up at this over here, this only seems to have the capacity to make 1 hydrogen bond. So if anything, it feels like that should be backwards. Oh. But then you could say, well, this is huge. Look at this. Lots of electrons there, lots of London dispersion forces. And this is tiny. Fewer electrons, fewer London dispersion forces. Yeah, but London dispersion forces are really weak compared to hydrogen bonds. So this is, I think this is one of the worst papers I've ever seen. I just don't like it. They picked a strange example, but that's their answer. Greater intermolecular forces, yeah, I'll go with that. Liquids stick together more than gases, so there must be more intermolecular forces. But more hydrogen bonds or stronger hydrogen bonds? They'd also give you stronger London dispersion forces. 6C, the hardest question on the paper. What's the formula of the salt? Well, normally when an acid reacts with a base, you get a salt plus water, but this is an exception. So let me draw out both molecules. So it seems that I've drawn them in a strange way, but that's because I'm going to try to explain what happens clearer. So acids lose a H plus, bronzodilary acid, so this H plus is going to go from here, and it's going to go over to that kind of ammonia-y end of that molecule. Actually, it's going to go onto the lone pair there. So what's happening is basically the same as a HCl plus ammonia. So the H is going over to there, which would make NH4 plus, and then the Cl minus. So I'm just doing the same thing but with longer chains. And there we go. I'm not even sure if you need the The charges, let's have a look. The charges are not necessary for the mark. Okay, yeah, that was a tricky one. Where's the water? There is no water. 7a, I'm not a big fan of these Hess cycles. Hess's law, where they're all lined up, I can do those, I kind of enjoy those. But these cycles make me scratch my head sometimes. So 7a, identified a type of reaction in step 1. Well, I'm adding hydrogen. So do they want addition reaction? Adding stuff? A and B make C. Or hydrogenation, because it's adding hydrogen. Not hydration, that's adding water. Or bromination, that's adding bromine. So I'm going to go with hydrogenation. Let's see what they say. Electrophilic addition or reduction. Okay, so adding hydrogen is reduction, but they'll accept hydrogenation. Oh, how benevolent. So 30% of people got this correct. Well, let's look at 13. So ethene is minus 1411, and hydrogen is the only other one on the table, is 286. So minus 1411 and minus 286. So if I burn ethene, I make that much, completely combust ethene, I make that much energy, and I make that much energy with the hydrogen. So I'm just going to add those two things together. You can't really burn oxygen, can you? I mean, you need a fuel for that. So what have we got? 1411, 286, that's going to be 796. So 1697, I think that's going to be kilojoules per mole. Are they fussy about that? Oh, it's kilojoules. My mistake, not mole. But there's no points for the units anyway. Still think that might be kilojoules per mole. Determine the standard enthalpy change of step 1. Okay, minus 1697, minus 1697. So this is minus 1697. So I'm going to do the clockwise arrows equal the anti-clockwise arrows, but it seems that I need a value for step 3, which is the combustion of ethane, but that's okay. I can just look that up in the table. Then I have step 2 and I have step 3. So ethane is minus 1561. Strange they didn't tip me off that I had to do that. So that's minus 1561, is that what I said? Yeah. Okay, so now I've got 1 plus 3. So it's going to be reaction 1 plus 3 equals that way round. So clockwise equals anti-clockwise. Equals minus 1697. So my value for 1 is going to be minus 1697 plus 1561. So what's that going to be? 136. Is that minus 136? Yeah, minus 136 kilojoules. Okay, so that's a Hess cycle. All right, 7D is challenging. I must admit, I had to look the answer up for this one. It's not in the normal style of the IB, but that's not an excuse. So why is the value accurate? Well, to me, accurate means it's close to the accepted value, but that doesn't fit with the style of the question. It could be considered accurate, well, they say, because it's based on a law, Hess's law. I'm not convinced that that's a great answer. No approximations were made in the cycle. I don't really like that either. Or Hess's law is a statement of conservation of energy. Okay. I think I would have lost that point. And approximate, well, maybe the values in the table, this one I could do, maybe the values in the table aren't exact. There's been some experimental errors when they made that, and they said there's no uncertainties reported. Every value must have an uncertainty. Is that right? Yeah, that's the first one. experimentally determined they had uncertainties. All right. That's it. I think in all my years of doing IB, I think that is my least, I think that is my least favourite IB exam. I think it's riddled with inconsistencies, problems, and even the odd wrong answer. So say Mr. Thornley. Bye.